Hello, everyone. We are talking about advanced training methods. Let's start. Our outline for today, we will talk about the optimizations and regularizations of neural networks. So let's start from gradient descent. A little revisit about gradient descent. So gradient descent, we are initializing our parameters. We are going iteration from k until convergence. We choose our step size of each iteration, and we update our parameters with regards to our gradients. Of course, it's not feasible to do a gradient descent on all the samples, all the parameters that we have in our huge networks. So what we do, we use the stochastic version of gradient descent by actually sampling random parameters and update them. Of course, we have assurance from some optimization theory that this will converge to almost the same or approximately the same one that's stochastic gradient descent. So we are actually updating the theta k1. The next iteration will be the existing value minus the step size or multiplied on unbiased gradient descent of our loss in k iteration. So actually what we are doing here, this is our optimization loss curve. So we are taking our parameters. So the function is function j, it's the variable of theta 1 and theta 0. So we are taking some we initialize our parameters, and then we are going forward our optimization loss until we reach our optimal loss minima. So how it's going practically? We use backpropagation, we compute our gradients. We need a differentiable function. We can use functions like argmax, hard binary, or other functions that are not tractable. If we kept this function, we do the smoothing version of this function. Yes, we use smoothness for backprop over these functions, or unless using a different way to compute gradients. So stochastic gradient descent, as we said, is gradient over entire data set, is impractical. So we take noisy steps and we estimate over some mini batches of randomly picked examples. Some tips about how to choose the mini batch, or actually mini batch is batch of examples that we are using for one iteration of our gradient update. So we will use as large batches as we can. Depends of the memory of our GPU that we actually can initialize. Yeah. So and one more tip is to crank up the learning rate when increasing the batch size. Yeah. So we need to fit our batch size accordingly, different size, different mini batch. So of course, if we're talking very huge batches, we need to increase the learning rate accordingly. Okay, so use small batches for small data sets. Yeah, if you have small data sets, so we will use small batches and not big batches because we want to use more iteration over each parameter. How to pick the learning rate? So This one is example of too big learning rate because we are not reaching our optimal minima. We are actually diverged from one, like it's oscillation. We are doing oscillation, so we are not converged here. So this means that this plot is show too big learning rate consideration. This one showed too small learning rate because we are trying to converge but not reaching our optimal minima. Yeah, so how to pick? Too big learning rate, we are diverged. Too small, slow convergence. So we no one learning rate to rule them all. We are doing it by a hyperparameter and by tuning to our specific data sets and architectures. Hint, start from a high value and keep cutting by half if the model is starting to diverge. And learning rate schedule, we want to decay the learning rate over the time. So we are multiplied by some fraction each iteration. So again, this is what was versus epochs. Good learning rate should converge in this style, and high learning rate can give us the convergence, but not to the optimal minima. Low learning rate will converge really slowly and can also not converging with to the minima. Very high learning rate can give us diverge. Yeah, it will be shown from the first plot. Okay, so gradient descent, this is great algorithm, very useful, but let's try to make it more, to make it better. What do we want to do? We will use momentum. Okay, so this is our curve. So what is it to do? HDD is like, you know, he's doing slips from here to here, from here to here, from here to here, from him to here, and which we are looking. So actually, we are not going to, we are orthogonal to the direction of the minimum. Yeah, and we want we are orthogonal to the directions of our yeah, optimum point, local point. And we want someone that will direct us, yeah, give us better direction for reaching the minimum. So actually, it's working like zigzagging, yeah. We are doing zigzagging and orthogonal, but with some slope, orthogonal slope, orthogonal slope, orthogonal slope. This is HDD, of course. What we would like to do, we want to avoiding sliding back in a force along high curvature. We want to go faster in the consistent direction to our local minimum. So stochastic gradient descent, this is the update rule. Yeah, so xt plus 1 is xt minus the gradient multiplied on step size. And while true, we compute our dx, and of course, x is minus learning rate on dx. But we can use also the velocity. And here we will use HGD plus momentum. So velocity, we actually define one more parameter. So the parameter is velocity. It's also, yeah. So we define our velocity, vt plus 1, it's p vt plus our gradient of xt. Yeah, so first we define the velocity vx to be 0, and we will compute our dx and vx and the learning rate, and our x will be the learning rate, and multiply our velocity. So the velocity is actually running mean of the gradients, and it will the rho or friction is typically we define it or to 9.0 or 9 or 0.99. So yeah. So what the problems that we can have that momentum can solve us. So the first problem is the local minima, like here, as you can see. So here is we can local minima, and we can be actually, it's very hard to avoid here, yeah? So we can stuck in this local minima and not reaching to our minima. So we need something for jumping this local minima. The second problem is saddle point, and the saddle point is you can see here. So this is local minima, this is local maxima. So here is very, in this surface, and this two surfaces is very easy to reach them. But if you have saddle point, the gradient in this point will be 0. So actually, it's like the gradient 0. We cannot, we are not progressing to the local minima. But the gradient here 0, but it's not local minima. Yeah, it's saddle point. So we need to, we don't know, because the gradient here is 0, we don't know which direction we need to progress, okay? So here gradient is in this point, and at this point gradient descent have a problem. Okay, so velocity, as we defined it as a logarithm, it's actually, it's combining a gradient at current point with velocity to get step used to update weights. So it's help us to find the actual step. So the gradient and the velocity together will combine and get the actual steps that we should do. So the momentum itself, it's how the momentum update, combine gradient at current point with the velocity to get step to use the update weights. And another way, we have some modification of the momentum. So the modification, So the modification momentum is Nesterov momentum, is one of the more, when we are talking about SEG plus momentum, we are almost, is identically to talk about Nesterov momentum because it's more feasible and better way to use momentum. Is like look ahead. So the point where updating using velocity will take us compute gradients there and then mix its velocity to get the actual offset update. So actually we using velocity, and here we're using the gradient for getting the actual step. Okay, so the Nesterov momentum is defined like that. So velocity t plus 1 is rho vt, so about the hyperparameter rho we talked before, minus alpha is our step size, and gradient in xt plus rho vt point. And once we compute the vt plus 1, we can compute xt plus 1 by taking xt and adding the vt plus 1. Yes, Sharon, please, if you have a questions, ask it. It's really annoying to looking on the chat. What does the velocity represent? What is the formula? I don't know when you asked, but velocity represents against velocity is 1. So this is the formula of the velocity. And velocity is represent one more indication to where our which direction we should go for reaching local minimum. Okay.
Yes, but my question is, we know the gradient is the derivative of the weight. So what is the velocity? How do we determine it?
Okay. So yeah, you're talking about the yeah. I didn't add the explicit derivation of velocity here, but okay. In my updated slides, I will add the explicit derivation of the velocity. Okay. Again, so what I wanted to that you will understand from here is that the velocity is one more. It's actually the one more parameter that help us to reach the local minima. Okay, because it's help us. It's one more vector that help us to define explicitly to where to go. Okay.
Okay.
Thanks. Good. So yeah. So again, so this direction of our function x plus pvt, it's actually our actual step. Yeah. So we are derivate our function in this direction. Yeah. And the vt plus 1 will help us to go this direction. Okay. And then change of the variables xt to xt plus vt, and we will actually do some rearranging. So vt plus 1 will be pvt minus alpha of if f xt. Again, I changed the variables. Yeah, for getting the function at the point. Yeah. So xt plus 1 will be as follows. Okay. Another questions, guys? Okay. So pair learning parameter. So gradients of different layers have different magnitudes. Yeah. So of course it depends on the architectures or on architectural considerations, and we should be aware that the gradients are not normalized. Yeah. So different units have different firing rates. We want different learning rates for different parameters. It's infeasible to set all of them by hand, by some intuition. Okay. How to do it? So again, the first algorithms that we talked, HGD and HGD plus momentum, the learning rate is the same for the all gradients among our architecture. These algorithms that we'll talk from now are actually calculating the gradients. The learning rate depends on the magnitude of the actual grading of the actual gradients among our network. It means that for the different layers, we will have different learning rate. Okay, questions? Guys, is it clear? Is it clear?
Yes.
Thank you. So, first we will talk about AdaGrad. So AdaGrad defined like that. We define grad squared for 0, and then we compute our dx for computing gradient x. So grad squared is actually dx, summing the dx in square for our all parameters. And then the x will be the learning rate multiplied by dx, and of course normalizing by np squared t of our gradients plus some constant. So we adding element-wise scaling of the gradient based yeah, of the historical sum of the squares of each dimensions. Yes, so actually for parameter learning rates of adaptive learning rates. So we have adaptive learning rates for each parameter. Okay, good.
Can you explain what is the shape of a grad squared? I mean, is it scalar? Is it a vector? Like when you multiply dx by itself?
It's scalar. I
Okay.
will, yeah, this is scalar. I will, in 1 minute, I will emphasize it more. Yes, grad square is scalar. It's parameter. Okay. Good. So this is actually how it works. So what happens with undergrad? So we actually progress along our steep directions is damped, yeah? We progress along flat directions is accelerate. So if our steep directions is damped and our flat directions, we are getting acceleration on them, it's actually for avoiding the problems of the saddle point or a local minimum, non-optimal local minimus. So the question number 2, what happens if to the step size over a long time? So as you can see, for the answer is here. So it decays to 0, okay? Questions? Okay, so let's revisit the undergrad and going to some more useful useful algorithms. So the gradient updates depends on the history of the magnitude. Parameters with the small or sparse updates have larger learning rates. Yeah, so it's depend on the gradient itself. Square root important for good performance. So it's important to define it. It's more and it's more tolerant. We have toleration for the learning rate. So it's actually it's not so what it means that it's not so it's not so crucial to choosing the best learning rate. So actually it's not we can start from most of the learning rates and we can continue, we can converge because we actually have auto adaptation of our learning rate. Yeah. So in this algorithm, it's not so important of what will be our initial hyperparameter of learning rate. Okay. And learning rate and data grad learning rate go to 0 among the time because when square goes to infinity, the undergrad learning rate going to 0, it means that we are actually converged to some point. So maintain the entire history of we maintain entire history of the whole gradient. Sum of magnitude of the gradients always increasing. We force learning rate to 0 over time, and it's hard to compensate for an advance. Okay. So some Aram's prop, it's actually some additional or improvement over the other grad. So it's the same is the same algorithm of adaptation of learning rate in each layer. Yeah, but the grad square is defined in another way. So that it's defined by decay rate multiplied by grad square plus 1 minus decay rate, and here we are defining on dx, and here we multiply it by dx 2 times. So what's the difference? So Aram's prop is actually cares about recent gradients and not about the old gradients. We don't need to keep all the history. Why it's better? What do you think? Guys, what do you think? Why it's better not to keeping all the gradients? Or maybe it's not better, maybe it's worse.
They were a lot of time. Like if it has been converging for a lot of time, it's forced to converge simply because the sum of all future, not future, past gradients is large by some point.
Yeah, but look again. So no. So actually, you can maintain your whole history. Yeah. So you know the history. You know what the gradients was in each iteration. Yeah. So of course, you know if you converge, not converge, it's not that depend. It's depend on the on if your derivation of each step of the loss is actually you can progress to something. So you actually changing your learning, your eventually you didn't reach the point. So it doesn't matter. So both of them is works. So in both of them, you goes until you are getting zero change. So you have not you have no updates more your gradients have no more updates. Yeah. So or your updates is minor. Yeah.
But by converging, I meant the learning rate converges to zero. Like it will approach zero just because we've learned for a lot of time, not necessarily equal. And then we'll effectively converge because our learning rate will be very low, even though we might not have reached a minimum.
Whereas you're talking about undergrad, no? Yeah. Yes. Okay.
RMS prop doesn't have that.
Yeah. So of course you're right. So this is the plus for the undergrad. Yeah.
That's a plus for RMS prop.
Yeah. Sorry, it is the plus for the RMS prop. So
yes.
and another plus for the RMS prop by not but by looking only on the recent gradients. Okay, so you don't need to keep all your map on the computer, yeah. So you don't need all the gradients. So you can actually your GPU memory is not stuck. Yeah. So you don't need to you actually use less memory. Yeah. Agree?
But the way we implemented it, doesn't it only remember the I don't know, the norm of all the past gradients?
Yeah, actually you're right, because in the first way how people implemented the undergrad, it was by keeping the all map of the gradients. Okay, but specifically by keep looking only on the norma, you don't need to edit to keep all the gradients. So actually the major benefit is from of Aaron's prop on the undergrad is by not the learning rate is not goes to zero. Yeah.
Okay.
Agree?
Yes.
Good. So it's have a good property because of the optimization of if you have some landscape change, and so otherwise if you don't use cares about the recent gradients, it's will be undergrad. Yeah. So this is the two additions or two benefits that we have of ARMS prop to over undergrad. So and the standard gamma is here is 0.9. Okay, so we talked about undergrad and about ARMS prop. Now we will talk about combining ARMS prop, that is the best algorithms that we have seen about how to about using adaptive learning rate algorithm for different parameters, and we will talk about and we will add the momentum, because we have seen that momentum can avoid some saddle points, local minima problems, etc. Okay, so what we want to use, we want to include bias correction term for initializing our mu and v, yeah, to zero, and default, we have default parameters are so using default parameters are surprisingly good, and learning rate, they say, still helps here, yeah, and Adam we use it first in SGD. So what is Adam? So Adam, we initialized first moment and the second moment. We going from we are going from t to number the iteration, compute the dx, compute the momentum. This is our first momentum, yeah, and this is the second momentum. Here we use our bias correction, and here we in the final we combine or AdaGrad or Arms Pro, depends on what we are multiplying here. Yeah, so what we are doing, we are using bias correction for the fact that the first and the second moments are estimated start from at 0. Yeah, so we also use momentum and adaptive learning rate for each parameter. So actually, it's the best algorithm that it's the most I don't know layer depend and layer depend, parameter depend algorithms that we have that works for the most cases works the best. First, in Adam, his major plus, you don't need to tweaking hyperparameter learning rate. You don't need to tweak it because most of the initialization you need to keep some reason to define the first some reasonable number, yeah, for the learning rate, and then it will be changed for it iteratively by the gradient. Okay, so this is Adam, and it's the best for the most cases. It's the best choice to start. Then we will choose the second priority is SGD plus momentum. So another option that you have, let's revisit to saddle point. Here we have the saddle point. We don't know what to do. We are stuck. What we want to do, we want to use noise. Our noise will help us to, so we can add to gradient noise, normally to use some noise sample from some Gaussian distribution. So we add to Gaussian noise to each gradient, and it can be it can be a savior for exotic model, yeah, of course, but it will help us to avoid saddle points. And it's again, this algorithm is it's not you know, it's actually Adam is the first choice. Gradient noise you can use, but it's not, it's exotic models. Yeah, for the most for the common models, Adam for the common CNNs, Adam works pretty good. So guys, please ask questions with regard to optimization. So we talked about SGD plus momentum. This is two algorithms without learning rate, adaptable learning rate. Then we talked AdaGrad for first algorithm with adaptable learning rate by gradients for each layer. The second was Arms prop, a modification without using the global history, only of the recent gradients magnitude. And then we talked about Adam. Adam was modification over Arms prop with the adaptable gradient for each iteration, plus we add the momentum for getting better convergence. And gradient noise, in the case of the saddle points, it can help us to avoid them. So what to use? SGD plus momentum, Adam are good first steps. Just use default parameters for Adam. It will great works. Don't not try to do some sophisticated things. Learning rate decay, always good. Decaying our learning rate over time, it's always give us better results because, you know, we are, as we converge, our gradient are smaller and smaller. If we want, steps will be smaller to smaller and smaller to reaching our local minimum. Guys, we finished our first session about the methods, optimization methods. Now we will talk about regularization in neural networks. Please ask questions with regards to optimizations if you have. Okay, so which regularization we have? So we will talk about early stopping, L1 and L2 regularization, auxiliary classifiers a little bit. We'll talk about the dropout and the most common batch normalization and the different variants of batch normalizations that we have. So early stopping, what it means. So let's see on error and number of epochs plot. So as you can see, our training is actually converging, but our validation suddenly starting to diverging. So this can happen from we have this kind of optimization can happen in practical way. So what we want to do in this scenario is to stop here, actually to stop to looking on validation set and to stop when our error or when our loss on the validation set will start to increase. Okay, so one of the criteria of regularization, of one of the way to define where to stop is looking on our validation set and looking where the loss is changing from decreasing to increasing. Okay, good. Okay, so L1 and L2 regularization. So of course, L1 and L2 regularization is actually the ways that we are our parameters. We are actually keep them. We are normalizing. Yeah, first one to normalize them by taking normal of L1. Yeah, so it's like it's you know square. Yeah, we have some square and all L2. So L2 is like the parameters will look in around the circle. Yeah. Okay. So L1, but we have two distinctions between two of them. L1 is encourage sparsity over our parameters. Okay, and L2 is discourage larger weights because we are centering in a circle. So we are actually more normalizing our parameters to be as closer to each other. And we actually can take in assumption that we use Gaussian prior on our weights. Okay.
A question?
Of course, great. Yeah.
So you say L1 encourages sparsity. Why would we want to encourage that to begin with?
This is a great question. Why we want sparsity? So we have a lot of algorithms that can benefit from the sparse neural network. We can. I will give you a few options for this. One, if you have some option to prune your network when it's very sparse. Prune it means for sparse network you can actually remove some tensors. Yeah, you can remove them some tensors in some specific way for making your model smaller. Okay, so and the second one, you have a lot of hardwares that can benefit from working with sparse tensors for more efficiently. Okay.
Okay.
So again, you can some of the algorithms can take your sparse parameters and or compute them more efficiently. Yeah, because you have a lot of zeros. So there are some hardware that can benefit from them. Actually, not compute, saving energy by multiplying by zero, not computing, yeah, efficiently do it. Another way is to pruning your network. Pruning, it means not the tensors that are zero, and eventually, yeah, you can disregard them from your flow, from your graph, okay? Yeah. So this is why you can. This is why you can try. You may wish to encourage sparsity in your network.
And in that case, I have to take like other steps in order to. Because I know sparse networks are prone to they're not prone to noises, but they're vulnerable to noises in input, because or at least on the first layer.
Okay. You are talking. I will rephrase. So you know that sparse networks are more vulnerable for the input noise. Yeah, this is what you're asking.
Yes.
Yes, you're right. In some cases, they're really more vulnerable. But in this case, we including to our training some noise that we are feeding to network, some noise. So we not training inputs, we training inputs plus some noise for making network amenable from this stuff.
Okay, I see. Thanks.
Sure. But again, it's more, it's more advanced tricks and hints that we use. But yeah, we will talk about these cases when I will talk about when we have a lecture on how to compress neural networks. So there I will talk about what we want to do to making the network more amenable.
Okay.
Good. So L1, L2, two ways to regularizations that we have. One another is using penalized confidence distribution. First, we do not want to overconfident model again for avoiding overfitting. Yeah, we prefer smoother output distribution. Why do we prefer smoother output distribution, guys? Ophir, now I know your name. Why we want it? What do you think? So we prefer smoother distribution because they're more tractable and it's easiest to compute guidance on them. Okay, so when we panelize confidence distribution, we get invariant to model parameterization. Okay, and once we train towards smoother distribution, and we panelize by their entropy. Okay. So our true label is one hot vector. Our baseline is like that, yeah, initialization, and our prediction classifier is yi plus u, and then we can use with some noise of 1 minus epsilon plus epsilon, and our mixed target will be like that. So it's more smoother, but it's smoother distribution, yeah, because we are not working with one hot vector, and we are working with values that are smooth. So of course, we predict the right value, but we are also smooth the other values. Is it clear, guys?
Yes.
Good. Okay. Okay, so now let's talk about dropout. Dropout is common way to actually it was common way in the first architectures, like when we trained MNIST and Cypher 10, we commonly used dropout. So how dropout works? This is standard neural network against some multi-perceptron. So after applying dropout, we actually in each layer randomly remove the connections, only on train set, so we are not changing the model, we cutting the paths, okay? So we're doing it randomly over iteration. So this is in one iteration, in the second iteration, it will be the other tensors that will be cut, yeah? But, good. And in the, okay, so we don't see it, but in the test time, we proceeding the all networks. So the dropout, all the removing of the connections is, we proceed only in training. In the test time, we are proceeding all the networks. So what we are doing, the complex and the co-adaptation probably do not generalize. So we force our hidden layers to derive useful features on own by taking less information in each time. And we sample from some, to power n possible related networks or subnetworks. Again, present with probability P, always present at the test time. Question about dropout, about L1 or 2, smoothing.
Can you go back one slide? At the test time, why the W, the weights, are multiplied by the probability by P on the right side of the picture?
No, this is it's W. It's not P. So it's a mistake. It's typo.
Okay.
It's typo. We are not using. We are, the probability of taking the tensors only used in training. In test time, we are multiply all the connections. Okay, so I will change. I will fix it.
Doesn't it make it that like the average amount of activation that reaches neurons is higher because you use more neurons or perceptrons?
Again, I did not see it.
If during training we only use, let's say, half of the perceptrons, and in each iteration different half, and then on the testing we use all of them. So that means the average activation of perceptrons from one layer is doubled because they get more info.
Yeah, but you're again, okay. So first, the ratio or the number of the tensors that we want to include, it's hyperparameter, and if you do it, if the number is too high, so you are not learning good, yeah, because you're not learning all the necessary parameters, yeah. The second one is some good intuition is to take 40% of dropout, not more. And again, you are actually learning all of them, yeah. If I understand your question, because you're doing stochastically, so you each time you're choosing the 40 parameter to remove, but you eventually go over the all tensors. You have the information from the all tensors, yeah.
No, I mean, if say I'm a perceptron on the second layer and there's 6 perceptrons on the first layer, and I use dropout of 50%.
Mm-hmm.
So in each learning iteration, I receive inputs from 3 perceptrons on the first layer.
Mm-hmm.
Their weights are adjusted accordingly, averaging over a lot of, like, each of them at each time participates with 2 other randomly selected perceptrons, and each of the layers will eventually learn or be learned to be some amount that corresponds to the fact that the second layer perceptron sees 3 perceptrons on the first layer. And then on the testing, it sees 6 perceptrons. So on average, it should get double the amount of activation, which means it should be probably saturated.
So you're talking about the different distributions that you different magnitude of
I think this is the reason there's a P in the right hand diagram here.
Yeah. So I understand. Yeah, you're right. Again, yeah. Ophir, yeah.
Yes.
Yes, Ophir. Yeah. So you pay attention, right? So the P is actually to given the right normalization. Yeah. So it's like you are normalizing your weights. So the difference, okay, so again, so this is not a typo. Again, we are not using the number of the passes remain the same, but we are changing the magnitude, okay? So we are using the P for factorization that we will have the same magnitude of distribution. Okay?
Okay.
Good. But again, so here the P is mean that you are taking which of the weights, and here the P means that you are taking the same P. It's compensation for different for that the magnitude will be the same. Thank you for paying attention.
No problem.
Okay, so the next what we will talk is it's about Bayesian interpretation of dropout. So actually, the Bayesian, in this course I'm not emphasizing about the Bayesian approach, but Bayesian approach is actually we are talking about it's not looking on the values of the values of the tensors, or it's looking on the distribution of each value to be in the network. Okay, so two common ways to use Bayesian interpretation of the dropout is variational inference for Gaussian process and Monte Carlo integration over a Gaussian process posterior. So I am not emphasizing the Bayesian interpretation of the dropout, but if you want, you can look on this blog that they're talking about how you can see on the dropout as a Bayesian regularizer. Okay, now we will start talking about Bayesian normalization. So most of the common neural architecture for classification. For the other cases, we will talk in the next lectures, and there are no use of it's problematic to use Bayesian normalization. I will explain why. But for image classification, specifically or especially ImageNet classification, most of the convolutional neural networks architecture, ResNet and MobileNet and others that achieve this sort of state-of-the-art results until now, use Bayesian normalization. Regularization for converging the model. So the first and the original interpretation of Bayesian normalization was proposed by Joffe and Christian Zeddy in 2015. So now first we will talk about the original interpretation of Bayesian normalization and what it should and why we think it works. Then we will give a few improvements or additions to Bayesian normalization. So, what is internal covariate shift? So, it means that if you have training distribution and our test distribution is shifted. So it means that you already trained for some distribution and the test you have another distribution of the activations. It can harm your performance because other distribution, it means it may lead to another prediction or actually harm the accuracy. So distribution of inputs to layer is changing during training. It's harder to train smaller learning rate. Careful initialization you should do there. Careful initialization means take a lot of time to tweaking the parameters. It's easier if distribution of inputs stay same. So I know for each distribution that I have, that for the distribution of my inputs of each layer will be the same one. It's better to converge. It's better to treat it. And more convenient way to optimization. So how to enforce the same distribution? This is a very good question. And okay, so what we want to do is to fighting the internal covariance shifts that we have seen 1 minute before, few seconds before. So a few alternatives to do it are based on whitening. So whitening can remove the internal covariance shift, but or we can remove it by nasty correlation. So the whitening, it's actually using PCA. Yeah, it's it's actually doing the dimensional. PCA, it's one of the dimensional way to do the dimensional reduction to the power input, yeah? To converting from the original axis to PCA axis. It means that it's smaller dimensional space. So it's slow because we have to do PCA in the whitening process. The other problem that we cannot backprop through the whitening because it's not tractable. So fixing by covariance shift by whitening, problematic. So next best alternative, we can normalize. What does it mean by normalize? Make mean 0, standard deviation 1. It's not eliminated in this case, we are not eliminating correlation between the data, but we normalizing our data for the same distribution. It's fast and can backprop through it because we know it. It's very easy to backprop through normal distribution, but we need to compute our statistics. Okay, so how to compute the statistics? We will go over the entire data set. It's too slow. ImageNet, 1 million parameters. What you don't really want to do to compute over 1 million parameters, 1 million samples, of course. So the idea is to use batch, or actually some subspace. Yeah. So we want to approximate our batch, taking batch, that it will be a good approximation of our data set, and then compute our statistics over all the data by using it on this one batch. Of course, you will ask me, someone like, I don't know, Ophir can ask me a question. So the question can be, Chaim, what is the size of the batch? Because it's also a hyperparameter. Again, so in the most cases for ImageNet, we know that the optimal size is from 128. It's enough to get enough statistics. But it's also a hyperparameter, so you should be aware about it. So not all the distributions should be normalized. We have some rare features that should not be forced to fire the 15% at the time. Yeah. So we want to let our model to decide how the distribution should look like. So even undo the normalization if needed. Yeah. So how our batch normalization works? So first we take our values, our samples, taking our mini batch, the same, yeah. We want to have two learnable parameters. Now we'll talk about them. And the output will be yi, it will be batch normalization layer that will be applied on our, with the gamma and beta parameters over the xi. So what we do, we're taking mini batch variance. We normalize the x, and now when we have also normalized x, we need to do what? Scale and shift, because of course not all distribution are the same. We know the structure, but not all them have the same number range, and we want some of them that will be in with the other mean. So how we do it? By learn gamma and beta over, this is the two learnable parameters of batch normalization. And then we applying our batch normalization over activation in the many batch, and then we can actually use it during training and then test it. Okay, so what has happened in the test time of the batch normalization? We want deterministic inference, of course. So different test batches will give different results. So solution, we pre-compute the mean and the variance on the training set, and then use them for the inference. Okay. So practically, we maintain running average of statistics during training. This is how it works. So in test time, we have our x. So it's n by n inputs and the outputs tensors. So we have mu j and sigma j running average of values seen during training, and running average of values seen during training 2 for mu and sigma. And then actually our intermediates will have mu sigma for d, and our x is n multiplied by d, and our outputs will be n multiplied by d. So the same input and the output dimension, of course. Okay, so this is how it works practically. So
we apply this method during the training phase.
We learn the parameter during training. We applied the learned parameter during training and test time.
Okay, I mean like the running averages. You said that during testing we would like to use specific averages.
Yeah.
So we collect the running averages during testing only and use batch averages during training, or do we also do that during training?
Again, I think that I understood, but ask again, please.
Okay, can you go one slide back? I think it'll be easier to point at stuff. So during the training, we learn the parameters denoted by Greek letters. No, that's actually bad. We learn beta and gamma, and
we learn beta and gamma depends on the statistics of mu and j.
No, during that time, do we also use running average and running variance, or do we?
Yes.
Okay.
Yes, of course. Yes.
Okay,
yes.
Thank you.
But I want to distinct here that during inference we do not we actually use the statistics that was learned for segments for beta and for scaling parameters. Yeah, that will be the same here, because we want that applying our learned parameters on the mu and the sigma will give us the same distribution. Yeah.
And during inference, we calculate running averages again, or do we use the thing we've learned?
We use the things we learned.
Okay, I'm talking about the mu and the...
Yeah, so again, so you're using a run average of the same value. You do not calculate again the statistics.
During inference. Okay.
Yeah, during inference, you use, by running average, it means that you use the values that's seen during training. You are not compute the statistics for the inference time again, independently. Okay.
Okay.
Because otherwise you will see another numbers. You do not, you want that you will applying the same. You want using you already learned the scale and shift parameters. Yeah. So you want that they will be fit for the scale for the inference in the same way, given fixed distribution. Yeah.
So basically, during the training phase, I learn, in parentheses, 4 parameters, but only 2 of them I learn using gradient descent, where the other 2 I just like accumulate the average values.
Exactly.
And I remember all 4 values and use all 4 values during the inference.
Exactly.
Okay.
Exactly.
Thank you very much.
Sure. Okay. So. Okay, so again, let's see how we modify the batch normalization for the convnets, because in convnets we also have feature maps. Yeah. So if we have fully connected, we have n input, n tensors in input and d tensors at output. So we actually we have mu and sigma for each output. Yeah, and gamma and beta for each output. So the scaling will work like that. And for the batch for the convolutional layers, then we have n input features, and we have c channels, and h by w it's our size of the feature map. So we want actually to have mu and sigma per channel. So each of our channel will have different mu and sigma and different gamma and beta. Okay? Clear, guys? Okay. Very good. So, 1 minute. Great. So now let's revisit the batch normalization and the difference. So in the batch normalization, we have for the convolutional neural networks, we have for the input x given by n input channels, c n inputs, c channels, and the hw our feature size. Yeah, we have mu and sigma. It will be actually 1 by c by 1 by 1. Yeah, and the other algorithms that we have, the other modification that was proposed by Ulyanov is using instance normalization. So the difference in instance normalization is that we have the same behavior for the test and for the train. Yeah, so we have actually x, our input x, n by c by h by w. So we have n, not depends on, we have for each n, we have a different mu and sigma. So for each n, so it's from pixel wise to input wise. Okay. So here we have actually pixel wise. Each pixel have a different mu and sigma. Maybe it's more accurate way an accurate way to use normalization. So comparison of our normalization layers. So in batch norm, this is we have for this is our batch normalization. Yeah. So we have for each C we have parameters. So in instance norm, we have for each one of them, yeah. And if we use layer normalization, so we have for each layer, actually we have a parameter. Okay. So, and one more, actually, the modification that we have on instance norm. So it's pixel wise. It's using a few pixels. So taking if in this instance norm we have for each one we have each pixel we have four parameter our four parameters. In group norms we have for a few pixels this parameter. A few they of course in the paper they use a few, 3, 4. They use a few options for doing that. Okay, why we need normalization, guys? So this is the distribution of activation before normalization. As you can see, this is actually where we have the zero. So we have not it's not symmetric, yeah. So this is what happens after normalization. So we have symmetric, the distribution from it's actually mirrored from 0. This is of course applied because we used well. So we all the negative numbers are going removed. Okay. Remember I talked about the correlation or correlation of the features. So batch normalization is not fitting batch normalization is it's not working on, it's not fixing the correlation. It's not fixing the correlation problem. Because in batch normalization, as you can see, this is the original data, this is the zero center data, and this is our normalized data. So it's not, it's correlated. They have correlated. But again, we talked about if we want to remove the correlation, Huang in CVPR 2018 proposed the correlated batch normalization. So it's actually they call it DBN. So it whitens the data using full covariance. So we're taking covariance, we're taking the matrix, the covariance matrix, yeah, and then we using the covariance, full covariance for decorrelate our numbers. So the xi will be using, this is the sigma, it's a covariant matrix, yeah, multiplied by xi minus mu. So in this way, we also use, after batch normalization, we have whitened data, so it's decorrelated. Of course, it's not this, again, batch normalization works great. So the correlation batch normalization can help in some exotic distributions and exotic cases. Most of the cases are DBN works the same like batch normalization, and the precompilation using this full covariance matrix is not needed. It's only taking more time. So, what the advantage of the batch normalization? It enables higher learning rates because it stabilizes our gradients are stabilized over. We talked about fixing distribution over layers. It's more resilient to parameter scale. Yeah, it's a regularized model making dropout unnecessary because we don't need here dropout. Once batch normalization was proposed, dropout is actually have no need, because batch normalization implies all the benefits that dropout had, and of course have much more benefits. And most SOTA CNNs, most convolutional methods that achieve state-of-the-art accuracy results use batch normalization. So practical tips for regularizations: we use batch normalization for fit for structures. We will talk about dropout only for good performance of recurrent neural networks next session. Entropy regularization, good for reinforcement learning also in the reinforcement session. And don't go crazy with regularization. Try with some small regularization and see the results, and only after trying to apply more hardest regularization, more more stronger regularization. Is all what I said was clear enough?
What's entropy regularization?
Okay, so so entropy regularization I didn't talk about it in this lecture. It's a teaser for the reinforcement learning.
Okay, and what's RNN?
Oh, this is also a teaser. RNN is recurrent neural networks. It networks with memory using for sequential for using with sequences for language models. And we will talk it like next lecture.
Okay.
So both of them, dropout and entropy, are used for now. They have a use after batch normalization only with non-CNN classification problems. Okay. So today we actually closed the all organization optimization techniques that we have for convolutional neural networks classification. Other domain neural network stuff, we will talk about their specific regularization in the appropriate lectures.
Any practical tip regarding L1 and L2 regularizations?
Yeah, practical tips. Using L2, it's works better, and don't go crazy. So adding this regularization only after you use the batch norm and optimizers like Adam and other stuff. So first choose the appropriate optimizers. And then see that you converge on the training set. Then see if you don't have overfit, and if you have overfit, it means that maybe you need to apply better, stronger regularization. Yeah, and this start from batch norm, and then you can also add L2 or L1, but only after them. Again, regularization it's not for. First, you need to the model will converge on training set. This is practically depend on which of the optimizers they use, and then for fighting overfitting, use batch norm, and then training some other like L1 or L2. It can be, of course, independently, so it can be in parallel. Yeah.
Okay, thank you.
You're welcome. So, we have a few minutes, so I will give you a few teasers. Why do you think, in which problems normalization can harm? Okay, so we talked about batch normalization, and it works very good. We fix distributions, remain the same over the network. It's very great. It's good, but we do some scaling. We normalize the we normalize the tensors. It works good to classifications problems. But where do you think it may have occurred some problem? Okay, I will give you some intuition. Let's say we want to predict some specific number. Okay, so we want to do regression problem. We want to predict. We want to synthesize. We want to synthesize image, or to give synthesize image. So we want to taking some that the output of the network will be image, not classification, or some specific image. Do you think that using normalization can work good in this case?
It's a problem because the consumer of the output results is the human eye, and like if we did classification, there would be a final step that translates things to a language whoever has to use it understands, which is like, this is the number you need. But if you want to actually see the picture, there's a problem because the human eye does not go through normalization.
Yes, Ophir, it's excellent answer. I will try to rephrase it a little bit. So actually, when we are talking about classification, we're talking about a relative problem. So we want to classify a specific class among other classes. So we are relative to other classes. So in this case, it doesn't matter that the nominal value of our tensor, but it's the difference between this value and other values in distribution. When we are talking about pixels, like you said, we're talking about the human eye. So we cannot rearrange the numbers. So we should be restricted to the computer vision, or to image processing standards that what should be the value of each pixel for getting the right color or the right texture. So in this case, we cannot use normalization. When your output is not classification, or it's not actually the prediction of the class, it's some regression problems. So it means that we predict specific value. We cannot use normalization from this method. Actually, it was what you have said. Why? So it's teaser for when we will talk about generative adversarial training. When we will in the lectures that we will talk how to synthesize the images, how to use neural networks for predicting the image itself. There we will use another regularization techniques. So hint: do not use Bayes norm when you want to predict specific output and not classification. But until then, our course from now until this point, we talked only about classification problems. Okay, so I give you some intuition for the next. Next lecture we will start talking about neural networks for text, for using for text language. Yeah, so and we will have 2 sessions about that. Then we'll talk about image synthesis, generative neural models, domain adaptation, and other very interesting things. So thank you very much for listening and who participated.